This is Mr. Pillar, ECET273 Modern Energy, Lecture number 11. Characteristics of a single and three-phase induction machine, based on Chapter 7 of the Square text and Chapter 14 of the Fardo-Patrick text. NEMA has 5 different motor designs, A, B, C, D, and E. They're specifically for squirrel cage induction motors. They are designed in terms of locked rotor torque, pull-up torque, breakdown torque, locked rotor starting current. Basically what we're looking here, each of the different types of motors, your general purpose are A, B, and E. We're looking at a percent of full load torque. Full load torque versus the percent of synchronous speed. Here's startup torque. Coming up here is our breakdown torque. And then final running torque right here. Remember, we are a percentage of synchronous speed. If we ran at 100% synchronous speed, our rotor wouldn't have access of be capable of doing what we need it to do. This is a percent of full load current versus percent of synchronous speed. Starting currents here for B, C, and D, 600% of full load. A is 800% of full load. We start to slope off here as we get up to synchronous speed. Alright, so B-type motor has the characteristics of B-type, 6 times rated current for locked rotor current. General purpose motor, medium locked rotor torque. This is, if you just bought a general motor off the shelf, you'd get a B-type. A, C, D, and E are pretty much motors that you'd have to purchase specifically and probably special order. A would have 8 times rated current. General purpose, again, higher rated breakdown torque, medium lock rotor torque, and a lower slip than B. So that means that with a lower slip, it means that the rotor current or the rotor speed is closer to the speed of the rotating magnetic field. C has a higher starting torque, used for compressors, pumps, conveyors, something that would have a large head pressure to get running. D has a high slip. It's not efficient. Has a very high locked rotor torque, but it's for impact loads, so it doesn't have to be efficient. It happens real fast and then waits. Happens and waits. So it would be something like a shear or a press. E is very similar to the B type, but again, 8.5 times rated current for an E type. I really want to point out here that we are talking about the design and not the code. The design right here, not the code. This is code level J. This is design A. This is code G, design B. Last lecture we talked about the codes. That helps us figure out kVA per horsepower, which helps us determine locked rotor current of that motor. What I want you to get out of this slide, torque is proportional to the square of the voltage. Okay, so what does that mean? Let's look at a quick example. A motor producing 1,000 foot-pounds of torque at V rated. What is its starting torque if 80% of the voltage is applied? Let's say it's rated at 120 volts and we're giving it 110. Okay, what would that do to our torque? Well, we end up with locked rotor current of 1, locked rotor torque of 2. The K's cancels, the V's cancels, so you end up with a ratio of torque of lock rotor 2 is equal to lock rotor 1 times 0.8 squared. So the percentage right here squared. We end up with, instead of 1,000 foot-pounds, we end up with only 640 foot-pounds available. Relationship between torque and slip. Really quick example here. A 4-pole machine, 100 horsepower motor produces 300 foot-pounds of torque when operating at full load. What's the approximate speed? Well, if you have half the load, your slip is halved. So we are working at 1.5% slip. So when we go into the locked rotor, or the rotor speed comparison to the synchronous speed, there's your synchronous speed of this motor, we end up with 1773 RPM. Alright, so motors are designed, we have design ratings on motors. So basically, what do those design ratings mean? Well, unusual service conditions would be ambient temperatures of greater than 40 degrees C, altitudes higher than 3,300 feet, voltages magnitude variation plus or minus 10%. Showed you a little bit of how that's going to affect your starting, breakdown, and pull-up torques. Variation of frequency. Remember, this is running frequency, not starting frequency, so variable frequency drives are another matter. Voltage magnitude imbalance, where the magnitude of A to the magnitude of B to the magnitude of C phase are different. That can be especially stressful. Alright, starting conditions. NEMA also defines frame sizes, right? Frame size, this would be a small frame, a medium frame, and a large frame range. The frame is the portion that bolts to the machine that you're running that motor with. If locked rotor current is approximately 6 times the rated current, well, that means that the portion of heating capability is the I squared. P equals I squared R, right? So the R doesn't change, the current changed, the power loss in heat, P equals I squared R, 36 times as much heating during locked rotor, which is starting current. So to give you an idea of starting times for the size of the motors, why does the size matter? Well, the size determines the amount of steel there to deal with the heat. It's a big heat sink. Slow acceleration or repeated starts can overheat a motor, right? So motors are rated for continuous rating. That means that 2 successive starts with full stop between, and initially the motor was at ambient temperature. So you come in the morning, the motor's been sitting all night, go ahead and start it. Oh, got to stop the machine, go ahead and stop it. Alright, you can go ahead and start it again. Don't try that again. That's all you get out of that one. Or, if the motor temperature is between ambient and rated, you only get 1 start. Now talking about starting also here, we can do what we call a Y start delta run motor. If we reduce the voltage at starting, we reduce the torque and the longer acceleration, but because we have lower voltage, that means there's less power being used, and that means that we'll have less heat to get her started, to get her rolling, and then we slowly bring up the voltage to get to full speed. That's okay. We will grab right here. Whoop. We grab the voltage from A to B, or to neutral, and as we look at it, we take a variac, and we'll go ahead and raise our voltage up within time to get us up to 277, and then drop us into 480 to run. That's a starting condition on that motor. So there you go. That's induction motors, single and 3-phase. Please take notes, go back through it, take notes again, come up with some questions, talk about it in lecture. Thank you very much.